Sai Ram. Welcome to this session of study of aldehydes, ketones and carboxylic acids, where we have already studied the nomenclature, structure and preparation of these compounds. And once we have these compounds ready, now it is the next aspect. What are the properties of these compounds? And when we discuss the properties, we mainly study and classify under two types, which is physical properties and chemical properties. Chemical properties generally deal with reactions that are associated with these compounds, whereas physical properties are the state of these compounds and various physical properties associated with that. So, before we get into the study of this, let us see the answers for the assignment that was given in the previous class. So, here is the first question for you, which is write the reaction for the preparation of acetophenone by Friedel-Crafts acylation reaction. Benzene is taken, acyl compound is taken, anhydrous AlCl3 is the catalyst that is taken, which is the Lewis acid. The carbonyl carbon, which is the electrophilic carbon, gets attached to the benzene ring which is present, and that gets continued further to form the overall carbon, which is acetophenone, generally if we take the example as CH3. Now, this is the general reaction which is represented. If, for example, if they ask you explain the reaction, then you may have to write a little explanation in English about the same reaction. Second one, give an example of a strong oxidizing agent. KMNO4 is an example which is given here, whereas you can also go with potassium dichromate K2Cr2O7. Mention the name of the product when propanamide undergoes hydrolysis. Since only the name of the product is asked here, the direct answer propanoic acid is given, but how do we get this propanoic acid is, suppose if we take propanamide, prop indicates 3 carbon system and CONH2 is the amide group which is present. To this, if I add water in acidic medium, H plus indicates acidic medium, water H2O, this forms a reaction like this where CO, the cutting actually happens here because of difference in electronegativity, and H2O splits up as H plus and OH. The OH attaches here, the hydrogen attaches to the NH2 to form NH3 compounds. So, this is the byproduct, whereas the main product for us is propanoic acid. So, important thing to understand here is that if we take a prop system here, propanamide, then we get propanoic acid. Suppose if we take ethanamide, we get ethanoic acid. So, the same carbon system retains in this type of reactions. So, these were various questions that we happened to study in the earlier class, and now let us get into the aspects of general physical properties of these compounds, starting with the state of the compounds at room temperature. So, at room temperature, methanol is seen in gaseous form, ethanol is seen in liquid form, and generally as the number of carbon atoms increase, the state becomes more and more towards solid. This we have already studied in the first year parts also, where smaller systems will be gaseous, slowly then liquids and then solids. But if you see the aliphatic carboxylic acids, you can see that till 9 carbon atoms they are all colorless liquids, which indicate that acids we cannot get it in gaseous form. We directly start with liquid forms, and maybe the higher carboxylic acids which are there will be solid in nature. So, seeing these general properties, we now see another physical property associated with this, and that is boiling point. The first thing, what is boiling point? The temperature at which the liquid changes into gases. So, here we see that generally all the smaller aldehyde, ketone, carboxylic acid compounds are of smaller size and they generally are in liquid state. So, couple of points are given here where aldehydes and ketones are higher than hydrocarbons and ethers. Please see the table where similar molecular mass compounds are considered, 58, 60 mass, that is the range that is considered here. And if you see the boiling points, there is a good amount of variation. Butane and methoxyethane actually has 273, 281, which is quite nearby. Then the aldehyde and ketone which is considered here, that is propanol and acetone, is quite similar to each other, 322, 329, and then the alcohol that is considered is pretty much high, that comes to around 370. Now, why such type of variations are there is what we need to see, where suppose if we take butane in this case. Now, in butane we have only carbons and hydrogen atom, so electronegativity will almost be similar. So, what force is available in this is nothing but van der Waals force. Now, what is van der Waals force? It is the force which is present between the atoms in a particular molecule. So, that van der Waals force will be available here. So, you need to supply energy. How do you supply energy? Temperature. So, that temperature is applied here and it is broken down. Similarly, if I go for the ether compound which is there, where for example, let me take methoxyethane. Now, in this methoxyethane, no doubt there is a difference of electronegativity between carbon and oxygen, but the fact here is on either sides the oxygen group is flanked by carbon groups. So, even if you try to differentiate its electronegativity, no doubt this is delta negative, but delta positive is dragged on both the sides. So, here the dragging of the electrons happens equivalent on either sides. Therefore, this also will have a similar boiling point, a little more probably, but almost similar. But when we come into the case study of the aldehyde and ketone, which is propanal, and let me take another example of propanone, which they name it as acetone in common naming. Now, here there is a good amount of electronegativity difference where delta plus delta minus. So, what does this do is it creates dipole. Di indicates two, pole indicates something that is apart. So, in this case, the charges which are there are separated between themselves. So, here along with the van der Waals force, there is also dipole-dipole interaction which has to be broken down, and that is why you need a higher temperature. What do you mean by supplying temperature? You are supplying energy to break open these bondings which are there to convert from liquid to gas. Now, boiling point does not mean change of compound. The compound is exactly the same. If you take propanol, it is propanal only. Only thing is liquid is getting converted into gas. So, in this case it was about breaking van der Waals force. In this case, along with van der Waals force, you also had to break open the dipole interactions which are there. Now, when I go to an alcohol, let me take propanol as an example, where no doubt van der Waals force will be there, but along with van der Waals force, this can undergo hydrogen bonding with fellow particles. Now, when I say propanol, it is not just one molecule of propanol, there are lakhs and crores of molecules of propanol. In fact, you know very well that one equivalent mass will have 6.022 into 10 raised to 23 atoms or molecules, which is actually equivalent to Avogadro number. So, when so many molecules are around, we know what is hydrogen bonding. It is attraction between electronegative element and hydrogen, and that hydrogen should also be attached to an electronegative element. Such a thing can't happen here, because this oxygen may attract with some hydrogen, but hydrogens here are not attached to electronegative element, but it does happen in propanol. So, what happens in propanol? There is an electronegativity difference also, there is hydrogen bonding also, and as usual it has van der Waals force. So, three types of forces are to be broken there: van der Waals, dipole-dipole interaction plus hydrogen bonding, and that is why a very high amount of energy is required, therefore higher temperature is seen. So, seeing all this, let us once again see the variations in temperatures that we have, where starting with hydrocarbons we have 273, 281. These two are less because they only constitute van der Waals. Then you have aldehyde ketone because of an additional dipole-dipole movement. Then alcohol is very high at 370, the reason being the presence of hydrogen bonding. Moving further now, let us talk about the carboxylic acids boiling points, which are having a similar concept with respect to aldehydes and ketones, but in carboxylic acid we see that the boiling points are much higher than all these compounds, for example aldehyde, ketones and alcohols. The reason is that we happen to finally discuss with respect to alcohol that there is a possibility of van der Waals force, there is a possibility of dipole-dipole interaction, there is a possibility of hydrogen bonding. Now, with a larger size of a molecule with multiple electronegative elements, the dipole interactions are much stronger here. Also, the possibility of hydrogen bonding here gets much stronger because this can have an interaction with oxygen. You can see here that hydrogen is attached to oxygen back. Also, this oxygen also can interact with this hydrogen. Why? Because what does hydrogen bonding say? It is the force of attraction between electronegative element and hydrogen atom, and that hydrogen atom should be attached to an electronegative element. So, there is a possibility of this interaction also as well as this interaction. So, the basic van der Waals force remains the same, excessive dipole-dipole movement because of two electronegative elements which are there. Excessive hydrogen bonding is also seen. So, therefore, naturally when so much of forces are there, you may need more energy to break this compound, break this liquid into gaseous form. So, therefore, carboxylic acids of similar molecular mass will have higher boiling point than the corresponding aldehydes, ketones and alcohols. Now, in this case we see a sort of a dimer interaction which is there. What do you mean by dimer is mer. We have heard this word mer in polymers, where mer indicates a single unit, di indicates two. So, for the stability of carboxylic acids, we have the intermolecular hydrogen bonding present in this compounds, where suppose if this is one molecule of carboxylic acid, let me write another molecule of carboxylic acid. It is just that the way it is represented I have changed. This is also RCOOH, this is also RCOOH. It's just that upside down I have written. That is because I just want to show how the bonding is taking place, where due to high dipole moments there is a hydrogen bonding present here, hydrogen with oxygen further attached to electronegative element which is oxygen. Similarly here also, attraction between hydrogen and oxygen, this hydrogen is again attached to oxygen. So, this sort of structures we tend to call them as dimers, and which means that individually getting a carboxylic acid will not be possible. Their stability is more stronger when they are formed like this as a dimer. So, all these factors lead to a higher boiling point of these type of systems. So, seeing these boiling point physical factors, now let us see how they are soluble in water. First things we have to see, are they soluble, and if yes, how much they are soluble. Generally we know that solubility in water depends on two factors. What are the two factors? One is how best hydrogen bonding takes place, because the advantage with hydrogen bonding is that it will be able to hold on to other substances. Second is the hydrophobic part. Now, for example, let me take say ethanal, a 2 carbon system, therefore eth, and the functional group is CHO. So, I have taken this compound. For boiling point, I used to consider other molecules and how is their interaction. Now, because I am talking about solubility with water, let me consider a structure of water. It's just that a little inverted form I have written. Now, what are the possibilities of bonding there? See, you can actually have this hydrogen bonding. How it is possible? Electronegative element, hydrogen, which is further attached to electronegative element. Please remember that this hydrogen bonding will not be possible. Reason being, this is electronegative, this is hydrogen, but it is not attached to electronegative element, it is attached to carbon. So, therefore, this bonding will not be possible in these cases, only this one. Now, which means that there can be some amount of interaction between aldehyde and water. So, they may be soluble, but the problem is the moment you start increasing, say suppose this becomes CH3CH2, which is propanal, then you slowly increase it and maybe you take butanal. What happens here is, with increase in C, the carbon groups, these are all hydrophobic groups, phobia means fear, all to say they want to be away. So, the one which is soluble in water is this part, and if it is a small molecule, the hydrophobic part will be pretty less. So, if I consider this as say ethanol, the hydrophobic part is pretty small. So, it may entertain some amount of solubility in water. The problem comes when the chain goes on increasing. So, with a larger hydrophobic group, the difficulty in solubility in water will be quite evident. So, that is where we see that smaller groups which are there will definitely be soluble in water, but as the size of the chain increases, the third point, if you see, the solubility of aldehydes, ketones and carboxylic acids decreases rapidly on increasing the length of the alkyl chain. The reason being, the groups which are being attached are hydrophobic and therefore they will not be entertaining solubility in water. If this was about the solubility in water, the next aspect is solubility in organic solvents. Are these compounds soluble in organic solvents? Now, we know very well that organic solvents are those compounds which are generally made up of organic compounds which are not ionic in nature. Ionic compounds, we generally consider them as inorganic, say for example water, which can split into H plus and OH minus. Now, people like benzene, ether, methanol and all these are organic compounds, and we know that in case of solubility, like solubles in likes. See, in case of charges, it is unlike charges attract, but here solubility, organic compounds will naturally be fairly soluble. So, aldehydes, ketones, carboxylic acids, all these three will be fairly or pretty lesser soluble in these compounds, but they do sense some amount of minimum solubility in these cases. Moving further, odor of this compound. Odor essentially means smell of the compounds. What is the smell of these compounds? The smaller aldehydes will have a sharp pungent odor. Pungent indicates a little bad smell as such. As the size goes on increasing, the odor which is pungent slowly becomes more or less fragrant, which is because when we consider compounds like benzaldehyde, they are actually sweet smelling compounds which probably, if possible, you can test it in laboratory. So, higher compounds are generally having a good smell. Aliphatic carboxylic acids have unpleasant odor. This you can actually analyze if you have seen vinegar at your home. Vinegar is nothing but a composition which includes ethanoic acid. So, you have a little unpleasant odor as such, where you will not be comfortable with that smell. So, higher acids are generally solids. We have studied that, as size increases, the state of the compound becomes solid, and solid compounds generally will not be having any odor as such. So, these are all the physical properties that we come across for aldehydes, ketones and carboxylic acids. Thank you. Sai Ram.